Chapter 12 deals with actually basically Wi-Fi. So this is one of the chapters I want to cover. Uh, Covers the basic characteristics of modern Wi-Fi systems, which most of you probably have at home, or certainly you're familiar with using the Wi-Fi system at UE. Um, so I'm going to break this lecture into a couple short different lectures. So basically, a Wi-Fi consists of what are known as access points, the wireless access points, and then there are can be several of these depending on the size of coverage desired. In particular for UE, there are several access points across campus, and then even multiple access points within Cook Center. These kind of work similar to actually the cellular telephone network. The different mobile stations will connect to the wireless access point with the strongest signal. These wireless access points are connected into the traditional internet. They're typically wired together, and then into this common wired network that's also runs throughout the university or at home. Your wireless access point is probably tied into your cable, or perhaps your phone line, or perhaps even over you might get your Ethernet or internet via a satellite provider. So again, modern Wi-Fi was originally intended, I think the first version actually, for just connecting to one device, primarily a computer. Of course, that's had to change over the years as now we've got multiple devices within a home, or certainly the university, that need wireless access, and more than just computers, streaming audio, streaming video, and again, a lot of you may actually get your entire you've cut the cable and get your entire um, um, uh, television video media over the internet. So access AP is short for access point. It's essentially the radio that communicates in both directions with the mobile stations. They also provide security, and then they can extend the range of the wired network that a user has access to. Mobile stations connect to what's called a basic service set over the wireless local area network, and the basic service set is identified using formerly the BSSID, or more commonly it's the SSID. This is the network name you assign when you set up your home Wi-Fi router. Um, uh, so downlink and uplink data transfer is much different. So I'll talk about uplink in a subsequent video. Downlink is from the access point to the different mobile stations. So that can be controlled just by the wireless access point. Individually sending, of course, it broadcast out the packet over the available radio network, but the packet is addressed for only a particular mobile system, and then it services each of the mobile systems in a round-robin fashion. So the sending can be done essentially with time division multiple access, and here it's on a packet-by-packet basis instead of time division multiplexing done within the packet. But one of the issues is, it's not a fixed number of time slots. The number of users can keep changing as people leave the region served by the access point or enter the region. You can also have the mobile systems actually go into sleep mode, in which case the wireless access point can throttle down communication to any client that's in a sleep mode. Um, So, how do you do this? Assigning a whole bandwidth to one user, of course, would not be the correct approach. Everyone wants access. Multiplexing among all users, again, that may not be the right thing to do because some mobile systems may have infrequent network use, while others served by the same access point may have a steady stream of traffic going out over the Ethernet, over the internet. So what's actually used is the access point develops a multiplexing matrix that's based on a number of conditions: the signal strength, the data transfer rate, and then will, based on this multiplexing matrix, will determine the number of packets that are addressed to a particular mobile system in a given time window. Every client that receives a packet from the access point has to acknowledge it. There's an acknowledgement period set aside after each packet transmission, after each downlink packet transmission for the mobile system to acknowledge packet reception. Again, a client with low data rate requirements will be allocated less bandwidth by the access point by adjusting the multiplexing matrix. Let's see. So during this time when this transfer is taking place, this is not a full duplex network. Actually, it's half duplex. So during downlinks, during a downlink transmission, uplink transmissions cannot take place. So that's another form of time division multiplexing that has to occur. Let's see, anything else here? Similar to in the cellular network, the access point actually transmits beacons periodically. I think maybe one every tenth of a second. So as mobile systems move within range or leave range, they can scan for these beacon signals to then actually proceed to make a connection to the access point. And then there are several steps here. Initially, the mobile system is in a scanning range, looking through a set of different frequencies for a beacon that's being transmitted by the access point. And depending on your mobile system, you may then be able to choose from available access points, or it may actually just, if you're roaming and already connected to a network, it will automatically connect to the access point associated with the strongest beacon. So there is some synchronization required here about the mobile systems have to know roughly when the access point is downloading information, and then the mobile systems also have to maintain synchronization because they acknowledge each frame. So that synchronization information is actually in the beacon, and so the mobile systems actually use that beacon to synchronize with the access point. And the beacon interval is every tenth of a second, and then consists of the beacon data packet. It consists of 50 bytes. There is a capability information field within the beacon that contains information about the different modes supported by the access point. Okay. So the beacons, users listen to the beacons to select an access point. Mobile systems can either be in one of two modes, can be awake or sleeping. In a sleeping mode, the access point will throttle down the data rate to that particular mobile system. Users need to inform the access point before going in sleeping mode. The stations have to wake up periodically to listen to beacon signals to find out if there's any data being held at the access point for them. And then there is a delivery traffic indication message, indicates that currently are in a low power or sleep mode, and have data buffered at the access point. Okay. So here's the packet format for Wi-Fi, which is also known as the IEEE 802.11 standard. And then there are different substandards, you know, A, B, G, N, you may have heard of, to support different data transfer rates. But here's the packet header. It consists of a preamble followed by the MAC header, followed by the actual network data, and then followed by the packet trailer. In the MAC header here, that's shown here, this bottom figure is actually comparing 802.11, which is the Wi-Fi standard, with 802.3, which is the Ethernet wired standard. You'll see there are several addresses in the 802.11 MAC header. These are to actually support not only the source and destination, but actually two mobile systems can communicate through an access point. So in that case, there's 3 addresses necessary, depending on the purpose of the packet. Other addresses that may be present are actually the SSID address. You know, all of the packets being transmitted have this similar, have the same header information, but the payload can be different, and then that's indicated by different settings, and the frame control and the duration / ID can actually be different. Of course, the payload, the network data will vary from depending on the packet purpose as well. Okay, and then here's some additional detail on that 802.111 MAC header. This was actually on the previous slide, and the header stopped right here, and then we had all the network data. This is showing a bit more information about the two bytes that make up the front of the header, the leading part of the header, the frame control. So it indicates here the actual protocol version that's being supported, the type of frame to describe its payload. They're called DS here. These are really access point fields to indicate whether it's from one access point to another access point. Typically for user data, both these are actually set to 0, and then there's another bit that's used to indicate whether this particular packet contains all the data for this transmission, or that it's part of a longer longer set of data that had to be fragmented, broken up into smaller packets. Okay. And let's see. Okay, this is showing characteristics of one particular access point. This is from a Netgear wireless access point. All of these support different modes of operation. So the original mode was a 20 megahertz mode that supported a data rate of 7.2 megabits per second. Of course, some older hardware only supports this mode. A faster mode was developed, a 40 megahertz mode that you know, may not be compatible with your older hardware. So they do have this 2040 megahertz compatibility mode that will support the faster data rates provided by some of the modern hardware, while still maintaining the ability to communicate with some of the original hardware that was built for the original Wi-Fi specification. Okay, so I think I'll stop this video here, and then we'll come back and talk about transfer, the uplink transfer, which is a bit more complicated.